So how do we study this? It sounds very scary because it's something that we don't understand. It is not conceivable by humans, right? So how do we actually understand it? So this is conventional reinforcement learning, where you just have an agent which is affected by the environment, and the environment basically sends feedback loops back to the agent, and the agent performs actions that change the environment, right? And this is just a normal Q-learning function where Q represents the reward that an agent would get when they make a particular action, right? You can study this using not just agent-based simulations, but these special agent-based simulations, which are called multi-agent reinforcement learning simulations, because you would want these agents to be considered as little humans on a computer, right? So how do you create little humans on a computer? You need some sort of learning there. So that's why we use multi-agent reinforcement learning. And with this, it's a step away from just traditional agent-based simulations. By the way, traditional agent-based simulations is how I first started back in 2016. And I moved on to doing multi-agent reinforcement learning because you can have heterogeneous objectives, and also increasing complexity in any model in a traditional agent-based model will actually lead to overfitting. As you might be aware, overfitting is such a great concern in any kind of machine learning problem, and that also happens with agent-based simulations. So you can actually use multi-agent reinforcement learning, because that way you don't actually have to hard code the agent's action into the program. The agents just choose whatever they want to do, and they will evolve over time, get more intelligent over time by learning from their environment. So this is basically an iterated presence dilemma game. It is a normal agent-based simulation. You can see that the incentive for any player to defect when they have defected previously is 1.71 times total cooperators. So red represents defect while the previous move was also defect. So eventually everyone ends up defecting. But if you actually decrease it a little bit, you can learn that there is a stable-ish state, like a global kind of stability that arises when you have a smaller number associated with the incentive to defect. But if you have something that's close to 1, you can see that everybody tends to cooperate. So cooperate is represented by blue, so you can see that everybody tends to cooperate when its incentive to defect is almost neutral. Right? So now this actually changes the meaning of money, because if you have many AI agents that are interacting on a system making game warps on each other, now this actually makes it such that the agent that is able to make or compute or solve for the most optimal strategy is the agent that is able to get the highest utility out of the system, right? So that who is able to complete the most optimal strategy? The one with the most computational power. So computational power will be akin to money in such kinds of systems, and it's rather inevitable that they actually come up with human inconceivable strategies, because the example that I showed you is just one way games can be warped. There can be n numbers ways in which games can be warped, not just between 2 players, but between n players in a multi-scale system, right? So you can imagine what kind of strategies and what kind of coalitions and cooperation methods will be formed in such systems.